This will begin a read of Chapter 4, Section 1. And in Section 1, we learn about the nature of energy. What is energy? Wherever you're sitting as you read this, changes are taking place. Light bulbs are heating the air around them, the wind might be rustling leaves, or sunlight might be glaring off a nearby window. Even if you're changing as you breathe, blink or shift position in your seat. Every change that occurs, large or small, involves energy. Imagine a baseball flying through the air. It hits a window, causing the glass to break, as shown in Figure 1. The window changed from a solid sheet of glass to a number of broken pieces. The moving baseball caused this change. A moving baseball has energy. Even when you comb your hair or walk from one class to another, energy is involved. Change requires energy. When something is able to change its environment or itself, it has energy. Energy is the ability to cause change. The moving baseball had energy. It certainly caused the window to change. Anything that causes change must have energy. You use energy to arrange your hair to look the way you want it to. You also use energy when you walk down the halls of your school between classes or eat your lunch. You even need energy to yawn, open a book, and write with a pen. Different forms of energy. Turn on an electric light, and a dark room becomes bright. Turn on your CD player. I guess you can see that this is dated a little bit. And sound comes through your headphones. In both situations, energy moves from one place to another. These changes are different from each other and differ from the baseball shattering the window in Figure 1. This is because energy has several different forms: electrical, chemical, radiant, and thermal. Figure 2 shows some examples of everyday situations in which you might notice energy. Is the chemical energy stored in food the same as the energy that comes from the sun or the energy stored in gasoline? Radiant energy from the sun travels a vast distance through space to Earth, warming the planet and providing energy that enables green plants to grow. When you make toast in the morning, you are using electrical energy. In short, energy plays a role in every activity that you do. What are some different forms of energy? An energy analogy. Money can be used in an analogy, and an analogy is a story or an example to help you understand energy. If you have $100, you could store it in a variety of forms: cash in your wallet, a bank account, traveler's checks, or gold or silver coins. You could transfer that money to different forms. You could deposit your cash into a bank account or trade the cash for gold. Regardless of its form, money is money. The same is true for energy. Energy from the sun that warms you and energy from the food that you eat are only different forms of the same thing. Kinetic energy. When you think of energy, you might think of action or objects in motion, like the baseball that shatters a window. An object in motion does have energy. Kinetic energy is the energy a moving object has because of its motion. The kinetic energy of a moving object depends on the object's mass and its speed. Kinetic energy equation. Kinetic energy in joules equals 1/2 mass in kilograms times speed in meters per second squared. KE equals 1/2 mv squared. In this equation, the symbol V represents speed. The SI unit of energy is the joule, abbreviated J. If you drop a softball from a height of about 0.5 meters, It has a kinetic energy of about 1 joule just before it hits the floor. According to the above equation, the unit J is equal to the combination of units kilogram meters squared per second squared. Kinetic energy equation. Solve for kinetic energy. A jogger with a mass of 60 kilograms is moving at a speed of 3 meters per second. Now, step number 1. This is what you know. The mass, m, equals 60 kilograms. The speed equals 3 meters per second. This is what you need to find in step 2, kinetic energy, KE. In step 3, use this formula. KE equals 1/2 mv squared. Step 4, substitute the values of m and v into the formula and multiply. KE equals 1/2 times 60 times 3 squared. This equals 1/2 times 60 times 9 equals 270. Determine the units in step 5. Units of KE, or kinetic energy, equals units of m times unit of v squared, equals kilograms times meters per second squared, equals kg, kilogram meters squared over second squared, equals a joules. Therefore, the answer is the jogger's kinetic energy is 270 joules. At this time, use the back of your note-taking sheet and work through problems 1 through 3. Potential energy. Energy doesn't have to involve motion. Even motionless objects can have energy. This energy is stored in the object. Therefore, the object has potential to cause change. A hanging apple in a tree has stored energy. When the apple falls to the ground, a change occurs. Because the apple has the ability to cause change, it has energy. The hanging apple has energy because of its position above Earth's surface. Stored energy due to position is called potential energy. If the apple stays in the tree, it will keep the stored energy due to its height above the ground. If it falls, that stored energy of position is converted to energy of motion. Elastic potential energy. Energy can be stored in other ways too. If you stretch a rubber band and let it go, it sails across the room. As it flies through the air, it has kinetic energy due to its motion. Where did this kinetic energy come from? Just as the apple hanging in a tree had potential energy, the stretched rubber band had energy stored as elastic potential energy. Elastic potential energy is energy stored by something that can stretch or compress, such as a rubber band or spring. Chemical potential energy. The cereal you eat for breakfast and the sandwich you eat at lunch also contains stored energy. Gasoline stores energy in the same way as food stores energy, in the chemical bonds between atoms. Energy stored in chemical bonds is chemical potential energy. Figure 3 shows a molecule of natural gas. Energy is stored in the bonds that hold the carbon and hydrogen atoms together and is released when the gas is burned. Figure 3. As natural gas burns, it combines with oxygen to form carbon dioxide and water. In this chemical reaction, chemical potential energy is released. Gravitational potential energy. Anything that can fall has stored energy called gravitational potential energy. Gravitational potential energy, GPE, is energy stored by objects due to their position above Earth's surface. The GPE of an object depends on the object's mass and height above the ground. Gravitational potential energy can be calculated from the following equation. Gravitational potential energy, again measured in joules, equals mass in kilograms times acceleration of gravity, and you should remember what that is from the last chapter, in meters per second squared, times the height in meters, or GPE equals mgh. In this equation, the acceleration of gravity has the symbol g. On Earth, the acceleration of gravity has the value 9.8 meters per second squared. Like all forms of energy, gravitational potential energy is measured in joules. Potential energy equation. Solve for gravitational potential energy. What is the gravitational potential energy of a ceiling fan that has a mass of 7 kilograms and is 4 meters above the ground? And step 1. This is what you know. Mass equals 7 kilograms. The height equals 4 meters. Acceleration of gravity is 9.8 meters per second squared. Step 2. This is what you need to find. The GPE, or gravitational potential energy. Step 3. Use this formula. GPE equals mgh. Step 4. Substitute the values of m, g, and h into the formula and multiply. GPE equals 7 times 9.8 times 4 equals 274. In step 5, determine the units. Units of GPE equals units of m times units of g times units of h equals kilograms times meters per second squared times m. Kilograms times meters squared over second squared equals a joule. The gravitational potential energy of the ceiling fan is 274 joules. Once again, at this time, you need to use the back of your answer sheet, of your note-taking sheet, or another piece of paper to answer questions 1 through 4. Changing GPE. Look at the objects in the bookcase in Figure 4. Which of these objects has the most gravitational potential energy? According to the equation for gravitational potential energy, the GPE of an object can be increased by increasing its height above the ground. If two objects are at the same height, then the object with a larger mass has more gravitational potential energy. In Figure 4, suppose the green vase on the lower shelf and the blue vase on the upper shelf have the same mass. Then the blue vase on the upper shelf has more gravitational potential energy because it is higher above the ground. Imagine what would happen if the two vases were to fall. As they fall and begin moving, they have kinetic energy as well as gravitational potential energy. As the vases get closer to the ground, their gravitational potential energy decreases. At the same time, they are moving faster, so their kinetic energy increases. The vase that was higher above the floor has fallen a greater distance. As a result, the vase that initially had more gravitational potential energy will be moving faster and have more kinetic energy when it hits the floor. This concludes the read of Chapter 4, Section 1. To summarize once again, energy. Energy is the ability to cause change. The forms of energy include electrical, chemical, thermal, and radiant energy. Kinetic energy. Kinetic energy is the energy a moving object has because of its motion. The kinetic energy of a moving object can be calculated from this equation. Ke equals 1/2 mv squared. Potential energy. Potential energy is stored energy due to the position of an object. Different forms of potential energy include elastic potential energy, chemical potential energy, and gravitational potential energy. Gravitational potential energy can be calculated from this equation. GPE equals mgh. At this time, you need to take out another sheet of paper or use the back of your note-taking guide to complete questions 1 through 7. And once again, this concludes the read for Chapter 4, Section 1.